Wong Chemistry channel. This is the part 7 of your 4.3 orbital overlapping and hybridization. So we've been talking a lot about the hybridization process and orbital overlapping, on how to get the hybridization process and also the orbital overlapping. Okay, so in this video, we will talk about the example that have multiple central atoms, and we will go straight into the example. Because by right, you should be extremely good in the hybridization process, whether it's having a lone pair or whether it's having a pi bond. Same goes to your orbital overlapping. You should be able to draw the orbital overlapping of your central atom that either having a pi bond or either having a lone pair. Alright? So, the first example that I have in this video is your HCOOH over here. So, as always, we will start off with your total valence electron and the Lewis structure of your HCOOH. The total valence electron of HCOOH is 18, and the skeletal structure shall look something like this. And by looking at this skeletal structure, we know that we have used up 8 electrons. 2 electrons in each single bond. Therefore, we minus 8. With the 10 valence electron left, we will octet all the terminal atom. But before we proceed, just want to let you know which one is your terminal atom and which one is your central atom. Your oxygen over here is your terminal atom. Your hydrogen also a terminal atom. Your hydrogen over here is also a terminal atom. That means both of the carbon and oxygen over here is your central atom. In the other words, in this example, we have 2 central atoms, which is your carbon and oxygen. Alright? So the next step is to octet your terminal atom, but knowing that your hydrogen is already duplet over here, therefore, we only need to put lone pair to your oxygen only. And the 4 electron left will be placed in the central atom, but you have 2 central atoms. So, which central atom will get the electron? We will put this remaining electron into the central atom that is more electronegative. Between carbon and oxygen, definitely oxygen is more electronegative. Therefore, oxygen will get the 4 electron to make it octet. So, oxygen right now is octet by having the 4 electron. Therefore, you are done with your total valence electron and your Lewis structure looks something like this. But the problem arises is you need to check your central atom. So your central atom, both of them, oxygen is octet by having 8 electrons around it. But your carbon is not octet. Your carbon having only 6 electrons around it. So how can I make this carbon octet? Simple, we are going to take one of the lone pair from the oxygen and make it as a double bond. Therefore, your final Lewis structure should look something like this. And this will be the correct Lewis structure in terms of octet, in terms of electron, in terms of formal charge. Alright? And after you have your Lewis structure, the next step, definitely electron domain as always. Formula of electron domain, guys, sigma plus lone pair. But right now we have 2 central atoms, so you need to calculate the electron domain for both of the central atoms. Therefore, for carbon, the number of sigma that you have is 3, the number of lone pair is 0. Therefore, you will have 3. Okay? While for oxygen central atom, bear that in mind, the electron domain, we always only find for the central atom. But right now, we have 2 central atoms. Therefore, we need to determine the electron domain for both of the central atoms. Carbon, electron domain calculated is 3. Oxygen, electron domain calculated is 2 sigma plus 2 lone pair around the central atom oxygen. So, you have over here 4. And once you have the electron domain determined, you then can move to the type of hybridization. The type of hybridization for carbon central atom is your sp2. Why is that sp2? because your electron domain calculated is 3. While for the oxygen central atom, the hybridization will be sp3 because the electron domain calculated is 4. From the sp2 and sp3, we then can determine the geometry. The geometry for the carbon central atom, sp2, will be trigonal planar. While for the oxygen central atom, which is a sp3, the geometry will be tetrahedral. Okay? For the sp3 is a tetrahedral, but bear that in mind, the oxygen having lone pair. Okay? And make sure you are going to calculate the electron domain and also the type of hybridization for both of this central atom. Okay? By using this correct Lewis structure. Make sense? And make sure you are calculating the electron domain for carbon and oxygen, the type of hybridization and geometry for both of the carbon and oxygen. Because both of this carbon and this oxygen, they are your central atom. Okay? So by that in mind, we always find for the central atom. And now, since we know the geometry of your central atom already, your carbon, which is a trigonal planar, should have this correct Lewis structure, where it should arrange everything in the shape of trigonal planar. While for your oxygen as your central atom over here, having a tetrahedral with 2 sigma bond and 2 lone pair, your oxygen geometry will be a V shape by having your lone pair over here. You have your tetrahedral, but your tetrahedral having 2 lone pair, so it should be in the V shape. And this is your most correct Lewis structure in the correct geometry. Okay? And by using this correct Lewis structure, the electron domain, the type of hybridization, and the geometry, we then move on to your hybridization process. Bear that in mind, the hybridization process is always for the central atom. And since we have 2 central atoms over here, we need to show the hybridization process for both of this central atom. Alright? And guys, in the previous video, before the hybridization process, we have extra one more step. What do we check? We check the formal charge of the carbon central atom. And the formal charge of this carbon atom as the central, the valence electron is 4. There is no lone pair, so minus 0, minus 4 bond. Therefore, the formal charge of this carbon is 0. And when the formal charge of carbon calculated is 0, then it's a simple question. Ground state will have no changes. Therefore, starting off with your carbon ground state. The carbon ground state having 4 valence electron that located in your 2s, 2, and also located in your 2p2. Looking at this central atom carbon right now, the central atom carbon having no lone pair, but having 1 sigma, 2 sigma, and 3 sigma. So, for the carbon central atom, 3 sigma bond represent 3 single electron. And then we have a pi bond, and 1 pi bond represent another single electron. Therefore, do we need the pair up electron? No, because the carbon central atom has no lone pair. So the carbon definitely not needing a pair of electron. That's why we will then excite one of the electron from the 2s to the 2p. Therefore, your carbon excited state shall look something like this, where in the 2s electron will change, the pair up electron will left with 1 single unpaired electron, while in the 2p will have extra 1 single unpaired electron that is excited from the 2s. Okay? And as you have determined, the hybridization of this carbon is a sp2. So we know that sp2 means we are taking 1 from the s and 2 from the p. Okay? Therefore, for your carbon hybrid state, we will be only taking 1 from the S and 2 from the P, forming sp2. We already determined this hybridization just now. Okay, that's why we already know that it's a sp2, 1 from the S, single electron, 2 from the P, single electron. What happened to this? This will be your unhybridized p orbital. Remember your pi bond? Unhybridized p orbital means you are going to have pi bond. And we can check this from the Lewis structure. That is your 3 sigma, as we agree. Okay, this is the pi bond, as we can see in the Lewis structure. See that? And that is the hybridization process for your central atom carbon. Now, we move to the central atom of oxygen. For the oxygen central atom, the former charge will be the valence electron 6 minus the number of electron in lone pair 4 minus number of bonding 2. Therefore, the former charge calculated is also 0. When the former charge calculated also 0, which means the ground state of oxygen in this case will have no changes. And as we all know, the valence electron of oxygen is located in 2s2 and also 2p4. Oxygen having 6 valence electron. Okay, next, knowing that your oxygen right now having 1 sigma bond, 2 sigma bond, and also 2 lone pair. So your oxygen having 2 sigma bond, which is 2 single electron, and 2 lone pair. 2 lone pair means you need to have 2 pair up electron in your hybridization process. And I hope you can see in your ground state, that is the 2 pair up electron that we need. Okay, because of this 2 lone pair, you need to have 2 pair up electron for your oxygen central atom. Therefore, your oxygen excited state, if you realize, will have no changes. We cannot excite the electron because we need the pair up electron in the 2s to become your lone pair, and also the pair up electron in the 2p to become your second lone pair. That's why the pair up electron will remain there. Alright? And obviously, that is your lone pair, that is your lone pair, and that is your sigma. So for your oxygen, the 2 lone pair is ready, the 2 sigma is ready. Bear that in mind, if you look at your ground state and excited state, it seems like no changes in terms of the arrangement of electron. But in fact, the energy of the electron actually changed. Therefore, the ground state and the excited state both must be written during the hybridization process, even though the arrangement of electron is not changing. Okay? Make sure you have both of them written down. Okay? Next, oxygen as the central atom, we have determined that the hybridization is sp3. sp3 means we are taking 1 from the S and 3 from the P. Okay? Therefore, the oxygen hybrid state over here will be equals to sp3. And your sp3, guys, obviously 1 from the S and 3 from the P. The one that from the S is a pair up electron. The first orbital from the P is also your pair up electron. And then you have 2 single electrons from the P orbital. Just a kind reminder, that is your lone pair, that is your sigma, sigma. Is that clear? Okay, I hope that is very, very clear. And make sure you are doing it together with me. Alright? And your hybridization process will not be complete without the ground state of your terminal atom. And looking at the terminal atom, we have 2 different terminal atoms, which is your oxygen and hydrogen. Therefore, we need 2 different ground state for oxygen and hydrogen. For oxygen ground state, the valence electron of oxygen is located in 2s2 and 2p4. And this is for our terminal atom oxygen. And we have another terminal atom which is hydrogen. So the hydrogen of ground state is the simplest ever that we have, because valence electron of hydrogen located in 1s1. Okay, and this is the complete hybridization process for both central atom carbon and oxygen. Since we have two central atoms over here, therefore we need to write the hybridization process for both of them. Okay, and next we will be going into orbital overlapping. So in orbital overlapping, we again start off with your central atom. We are going to start off with both of the central atom in their hybridized orbital and in the correct geometry. Okay, so let me start off with the carbon central atom sp2 in trigonal planar. So that is my sp2 for my central atom, the first one, which is my carbon. Okay, so done with your central atom carbon, we always say we focus on the central atom first. So another central atom is your oxygen with sp3. Looking at this sigma is between the central atom carbon and oxygen central atom. So oxygen is a sp3 in tetrahedral. In the other words, one of the sp3 hybridized orbital will overlap with the sp2 hybridized orbital to form this sigma. So the first sigma that I will draw is the orbital overlapping between sp2 and sp3. So your sp3 is in the shape of tetrahedral. Knowing that that is your sp3 of your oxygen central atom. So make sure you label everything clearly. Okay, and the first sigma that you form is between your carbon and oxygen as the central atom and overlap head to head to form a sigma bond. Guys, bear that in mind, when it's a sigma bond, it must be end to end or head to head overlapping. End to end and head to head overlapping means they must be 180 degree or they form a straight line. So make sure your sp2 and sp3, they are forming a straight line. That is what we call end-to-end overlapping to form a sigma bond. Next, since oxygen having a lone pair, I want to position the lone pair first. It's a tetrahedral. If you remember in the video that we discussed about central atom that having lone pair, for a tetrahedral, the lone pair can be located in any of the sp3 lobes. Okay, so I can put according to my Lewis structure, my lone pair is located down here. So bear that in mind, lone pair is a pair of electron in opposite spin without even overlapping. Okay, that is my lone pair. Done with the lone pair, the next that I want to draw is my hydrogen because it's the easiest. And we know that hydrogen will overlap end to end by using the 1s orbital. So look very carefully, the sigma bond between carbon and hydrogen is between this carbon and a hydrogen over here. Knowing that your hydrogen is a s orbital. So your s orbital 1s coming from the hydrogen forming the second sigma we have. Alright. Another hydrogen will overlap with the oxygen central atom, this sigma. Okay. So your hydrogen will be located over here. This is the 1s orbital of the hydrogen atom, forming the sigma bond with a pair of opposite spin electron. See that? So we are pretty much done except this oxygen and carbon. So in this oxygen and carbon, we have a sigma and a pi. So let's draw the sigma bond first. So oxygen, everybody knows that, is a 2p orbital. So oxygen having a 2p orbital. And that is my 2p of my oxygen. Overlap end to end to form a sigma bond. Okay, next we are going to draw for the pi bond. If you remember, pi bond is a sideways overlapping and the p orbital must be parallel to each other. Okay, so it's either like this, like this, like this, or it can be even like this. Remember? Okay, so we are going to draw a pi bond between the carbon and also the oxygen, the pi bond over here. So, for the oxygen, it's still a 2p orbital. Okay, for the carbon, also a p orbital. Remember your unhybridized p orbital? that is the p orbital that will form a pi bond. Kind reminder, the electron in the 2p orbital and the p orbital must be in opposite spin so that they can overlap and form a pi bond. Okay, and that's it for your HCOOH orbital overlapping. Simple. And I think you will understand very clearly if you have watched all the video from part 1 to part 6 before watching this part 7 video. Okay? And everything will look better when you start doing it together with me, not watching the video and eating popcorn. Alright? So make sure you watch the video and do it together with me. Then you will understand why the structure look like that. Okay? The second and also the last example for this video that having multiple central atom is your CH3NH2. As always, we will start off with your total valence electron and Lewis structure. Total valence electron calculated 14. Okay, and the skeletal structure for this compound is something like this. Carbon single bond with all the hydrogen, and then the carbon will be holding a single bond with nitrogen. Nitrogen holding 2 hydrogen, like this. So this is the skeletal structure. Looking at the skeletal structure, how many single bond I have placed in? We have placed in 6 single bond. 6 single bond means I will minus 12 over here with the 2 valence electron left. But we have 2 central atom. Looking at both of this central atom, which central atom is not octet yet and which central atom is more electronegative? Which one will have the ability to pull electron towards itself? Carbon having 8 electrons around it, nitrogen having 6 electrons around it, and nitrogen is more electronegative. That's why the 2 electrons left will be placed on nitrogen as a lone pair. Minus out the total valence electron 2, then you are done with the total valence electron. And also, both of the carbon and nitrogen right now achieve octet. Clear? Next, we will then look for the electron domain by using the formula sigma plus lone pair for both carbon and also for nitrogen central atom. So for the carbon central atom, we have 4 sigma around carbon over here. Okay, and we have no lone pair. So the electron domain for carbon in this molecule is 4. While for nitrogen, the sigma is only 3. We have 1, 2, 3. So 3 sigma plus 1 lone pair. Therefore, the electron domain for nitrogen is 4. From the electron domain, then you can determine the hybridization. The hybridization for carbon, due to the electron domain is 4, therefore the hybridization is sp3. While for the nitrogen, the hybridization also sp3 because the electron domain are the same. Therefore, both of them will have a basic geometry of tetrahedral. Bear that in mind, the tetrahedral is the geometry of your sp3 hybridized orbital, not for the molecule. Okay, so we can redraw your Lewis structure where carbon will be in the shape of tetrahedral. So your carbon in the shape of tetrahedral will have your hydrogen bonded. And your carbon will be bonded to a nitrogen that having a lone pair with trigonal pyramidal. Okay, remember when you are having a tetrahedral and then you have a lone pair, so you will substitute one of the bond with lone pair. That is your trigonal pyramidal. So this is the most correct Lewis structure that you can draw for your CH3NH2 in the correct geometry. Okay, so from the correct Lewis structure, moving to your electron domain, moving to your hybridization, then we can move on straight away to your hybridization process. So, for the hybridization process, as always, we will draw for both of the central atom. Bear that in mind, we have two central atoms right now. Therefore, your hybridization process that we are going to draw, we must do for both carbon and nitrogen because both of them are central atom. Okay? And as always, before we start for the central atom carbon, what do we need to do? We need to determine the formal charge. So the formal charge for carbon in this case is 4 minus 0 minus 4. So you have the formal charge is 0. When the formal charge is 0, means there is no changes in the ground state. Starting off with your carbon ground state. The carbon ground state will have 4 valence electrons that located in your 2s2 and also located in your 2p2. Alright, take a quick look at your central atom carbon. Your central atom carbon having no lone pair, having no pi bond, only having 4 sigma bond. So since your carbon having 4 sigma bond, which means we need to have 4 single unpaired electron. Agree? So we need 4 single electron. Looking at the ground state of your carbon, we have a pair of electron and 2 single with an empty 2p orbital. So what do we do to achieve the 4 single electron? Simple. One of the electron in the 2s will be excited into your 2p. Alright? Therefore, your carbon excited state shall look something like this, where in the 2s, we only have 1 electron left, while in the 2p, you will have 3 single unpaired electron in each of the orbital. Okay, that will be your excited state of the carbon. And since in the previous step, we have determined the hybridization of carbon is sp3 according to the electron domain. Therefore, we need 1 from the s and 3 from the p. Can you see that? Resulting your carbon hybrid state shall look something like this. Your carbon hybrid state will be forming your sp3 hybridized orbital that taking 1 from the s and 3 from the p. And in each of the s and p will have 1 single electron. And what is this 4 single electron used for? Remember your 4 sigma bond? That is your 4 sigma bond. Okay? Simple. So this is the hybridization process for central atom carbon. But we are not done yet. Why we are not done yet? Because we have 2 central atoms. We have another nitrogen. Looking at your nitrogen, guys. Nitrogen having 1 sigma, 2 sigma, 3 sigma. Nitrogen having 3 sigma, which means we need 3 single unpaired electron. And don't forget, nitrogen having 1 lone pair. Lone pair means what? Lone pair means I need to have 1 pair up electron. Okay? And before anything, for the nitrogen, as always, you need to calculate the formal charge. Having the valence electron of 5 minus the lone pair 2 electron minus 3 sigma bond that will give rise to a formal charge of 0. When the formal charge is 0, it means there will be no changes of the nitrogen ground state. Where we know that the valence electron in the nitrogen ground state will be at 2s2 and also will be located at 2p5. That is the 5 valence electron in nitrogen located. Okay? And looking at the 3 sigma bond that you need and 1 lone pair that you need, can you see the lone pair already? That shall be your lone pair. And that shall all 3 be your sigma. So any changes in your excited state, there shall be no changes in your excited state for your nitrogen in this case. The excited state shall remain the same. Even though it's the same, like I said previously, we still need to redraw it. Okay, that is the pair up electron that you have in the 2s and then the 3 single electron that you have in the 2p. Make sense? Okay. And last but not least, the hybridization of nitrogen that we have determined is your sp3. In the other words, we are taking 1 from the S and 3 from the P. Therefore, your nitrogen hybrid state is your sp3 hybridized orbital, that we are taking 1 from the S and 3 from the P. And the first one from the S having a pair of electron, and then the 3 from the P having 3 single unpaired electron. I hope you remember that is your lone pair, that is your sigma. Is that clear? Simple. And all that is actually based on your correct Lewis structure. So no matter what, your Lewis structure must be correct at the beginning. Okay? And of course, we only have one terminal atom over here. All the terminal atom is hydrogen. Therefore, your hybridization process will not be complete without the ground state of the terminal atom. And the ground state of terminal atom right now is hydrogen. Your hydrogen ground state is located at 1s1. Therefore, you have your 1s that having 1 single unpaired electron. And that is your complete hybridization process for CH3NH2. And remember to draw the hybridization process for both of the central atom, your carbon and your nitrogen in this question. Simple, easy. From the Lewis structure and the type of hybridization with the correct geometry, we then can move on to your orbital overlapping straight away. Okay, we can do the orbital overlapping without using the hybridization process. What important is having your correct Lewis structure and the hybridization of the central atom and also their geometry. Okay, it's not needed to do the hybridization process before the orbital overlapping. We can straight away draw the orbital overlapping. Okay, and let's start off with my carbon central atom, which is sp3 in the shape of tetrahedral. So that is my sp3 for my carbon central atom. Okay, so make sure you label all of them sp3 and label the carbon. And like I say, after we are done with the central atom, we need to draw for another central atom. The nitrogen also is a sp3, and between carbon and nitrogen, we have a sigma. In the other words, one of the hybridized orbital of sp3 carbon and one of the hybridized orbital of the sp3 nitrogen need to overlap end to end to form the sigma bond. Okay, so the nitrogen sp3 will again be in tetrahedral shape. Okay, but one of the sp3 must be overlapped end to end with the sp3 of carbon. So this is my nitrogen and this is the sp3 of my nitrogen. And I hope you can see your sp3 right now is in the shape of tetrahedral. Okay? And that is my first sigma between the sp3 and sp3 of the carbon and nitrogen. And we are done with that. And since the nitrogen right now having a lone pair, we position the lone pair first. It's a tetrahedral that having the same bond angle 109.5 degree. Therefore, the lone pair can be positioned in any of the sp3 hybridized orbital. So put a pair of electrons without even overlapping. That is your lone pair. Okay? And then next, the carbon will form a sigma bond with 3 hydrogen. Can you see that? So all the 3 sp3 hybridized left will overlap end to end with the 1s orbital of the hydrogen, forming the first sigma between the hydrogen, another sigma between the carbon and hydrogen, where your sp3 hybridized orbital overlap end to end with the 1s orbital of the hydrogen. Last but not least, another sp3 hybridized orbital overlap with the 1s orbital of hydrogen, forming a pair of electron, your sigma bond. Okay, the nitrogen also having 2 sigma bond with hydrogen. So the 2 sp3 left over here in the nitrogen will overlap end to end with the 1s of the hydrogen. And this is the orbital overlapping of your CH3NH2 by using the Lewis structure to calculate the electron domain and determine the hybridization. From the hybridization, we know the geometry of the hybridized orbital. And from that, we can draw the overlapping to form the sigma bond and also the position of lone pair in this case. Okay? And that's it for this video. What makes it different is, in certain molecule or in certain compound, you have more than one central atom. When you have more than one central atom, in this case, like your carbon and nitrogen, you need to have the hybridization process for both of the central atom and also the hybridized orbital for both of the central atom in the correct geometry. Okay? So make sure they are in the correct geometry of tetrahedral, the correct geometry of tetrahedral for your carbon and nitrogen in this case. Okay? And the rest of the thing is actually the same. Make sure you overlap them correctly. Make sure you label every single thing that you draw. Okay? And if you still have any question about orbital overlapping and hybridization process, drop it in the comment below and I'll get back to you as soon as I can. I really hope that this video helps you to understand more about hybridization process and orbital overlapping. Make sure you like the video and subscribe to my channel. Thank you for watching and I'll see you again in the next video.